Welcome to the online marine seismic data processing course. In this video, I'm going to talk about Seismic Unix, which is a free seismic data processing package. Basically, if you're not familiar with processing seismic datasets, this software package can give you a good start to work with seismic datasets. Content for this presentation is I will start with a brief introduction of what Seismic Unix is and where you can download it from. Then I will show you some QC displays produced on the synthetic data using Seismic Unix. Then I will show you some real 2D seismic data examples, and then I will show you the marine seismic data processing sequence. Okay, so basically Seismic Unix is an open source seismic processing package. It aims at delivering a robust and efficient seismic reflection software package dedicated to education and to permit the processing of moderate size 2D seismic datasets. So basically with this package you can easily process some of the small or moderate size 2D seismic datasets. This is the link where you can download this software and all the information related to Seismic Unix. One thing I would like to mention here is that all the information related to the software is in its manual. So if you want to really understand every bits of the software, you need to go through the manual in detail. Okay, so I'll start now with the generating QC displays on synthetic data using Seismic Unix. So the first thing is the 1D bandpass filtering. So before that, so this soup plane. So soup plane is the command that can create synthetic dataset, a common offset data file with up to 3 planes. So as you can see that when you use this soup plane command, it produces these 3 planes, the one horizontal and then these other dipping planes. And SUXWIGV creates a wiggle plot, wiggle display, and SUXImage produces a interpolated display. So if you want to see the headers inside the soup plane, so if you use SURange piping soup plane, it will give you all the information related to this dataset. So when you run this command in your terminal, SURange soup plane, it will give you the information, which here it says there are 32 traces here, and these are the headers for the traces 1 to 32, and the offset for each of these traces is 400 meters, and the number of samples is 64. And the time and the sample rate is 4 millisecond. So this is your input. Now you want to apply some kind of bandpass filter. So if you apply a low pass filter, you can use this script. So basically I'm not going to go through each of these individual scripts. This is just to demonstrate that yes, you can generate these displays and apply these processes. So yeah. So this is a low pass filter. This is a high pass filter on the right. And on the left is a band pass filter, like starting at 10 Hertz, it stops at 20 and then ends at 30 Hertz on the higher end. And then the slope is from 30 to 60 Hertz. So you can generate or you can apply this process of band pass filtering on your data using this script. And now if you want to reject some frequencies, so this is a band reject filter display here, and if you want to just remove particular frequency, so you can apply a notch filter. So this is a 60 Hertz notch filter here. Okay, this is another application. You can apply a butterworth filter. So instead of having linear slopes, you have curved slopes. So it's a little bit better filter. So that's 1D bandpass filtering. And this is a demonstration of you can perform a Taupy transform. So basically a linear event in your XT space is mapped to a point in your tau p space. Tau is the zero offset time and p is the slowness, which is 1 over velocity. So on the left is your input data, and in the middle is your data with further interpolation, because when you do the tau p transform you need to satisfy the aliasing criteria. So here you had, like, if you do the SU range, you can see how many traces, and so here you have got 32 traces, and then in the middle display you have got 120 traces. So there are like 3 traces interpolated in between every 2 traces. So this is just to avoid aliasing issues, otherwise you will see aliasing in your final results. So yeah, so you can use this script to generate the Taupy, to perform the Taupy transform. Now this is another example of how you can add random noise. So on the left is your input, in the middle you have like Sn equals 2, so you have like either 2% noise added. So this middle display is with 2% noise, and then the display on the right gives is after 10% noise added. So it looks quite noisy now. Now, a very important thing in seismic data processing, whenever you apply any process, you need to look at the difference displays in order to see if you're not leaking any primary energy. So yes, you can perform differencing using these scripts. So here is your input, and the middle is with noise added, and the last display is with the difference of the input and the output. So that's the difference. That's how you generate the difference displays. Now the 1D Fourier application. So on the left is the input, and in the middle is your amplitude spectrum. So this is X and this is time, and here you have X and the frequencies, because it's a 4 millisecond data set, so your Nyquist frequency will be 125 Hertz. So each of the trace, for each of the trace you have an amplitude spectrum and the phase spectrum. So this is how you can generate the amplitude spectrum and the phase spectrum. Normally we display an average of the amplitude spectrum, so we have like average value for each frequency, for the amplitude and for the phase. Okay, so this is to demonstrate the 2D Fourier transform. So your horizontal event on your XT domain will be mapped as a vertical, because the tip is 0, so it's mapped as vertical here. So just remember, as a rule, horizontal event in XT is mapped as vertical, and vertical event in XT will be mapped as horizontal. And of course the other 2 events, one of the steeply diving event is alias. So you see this aliased energy here. So this is 1D Fourier transform, and this is when you perform the 2D Fourier transform using SUSPAC K1 K2, and here you use SUSPAC FK. Okay, and this is just to show you how you can perform Hilbert transform. Normally the Hilbert transform is used in land data processing. I've never used it, so I cannot comment much on that. This is the application, how you can generate different trace attributes on a synthetic vibrosis. So on the left you have the synthetic vibrosis sweep signal, and you have got your instantaneous amplitude, instantaneous phase, instantaneous frequency, and time frequency plot. So these are the scripts used to, the commands used to generate these plots. So yes, you can use these to create your displays. So this was all about generating the QC displays on the synthetic data using Seismic Unix. So in the next few slides, I'm going to show you the generating the QC displays on real seismic dataset using Seismic Unix. Okay, so for this, the QCs in the next few slides, I'm going to show you will be from this dataset, the mobile ABO Viking Raven line 12, which is freely available. If you click on this link, I will put this link in the caption, so you can use this link to download this dataset. When you click on this link, this page will pop up, and then it will give you the following files. So the most important file is the file that contains the seismic data, so seismic.segvi. So segvi is a standard format for sending or receiving, keeping the seismic data for exchanging, basically. And the other, the mobile well logs, which we are not interested at the moment. And then the farfield.dat is a farfield signature, which will be which is not shown at the moment, but it will be in my next video. The application of the farfield signature for doing the debubble and zero phasing. So this is how your farfield signature looks like. So here you can see your primary, and this is the source ghost. So source ghost is included in this farfield signature. Okay, so these are the details of this seismic data, the 2D seismic line. So it's a 25 kilometer long profile, and there are like 1012 shots, number of channels 120 on the streamer, and the receiver interval is 25 meters, shot interval is 25 meters, the nearest offset is 262 meters, cable depth is 10 meter, gun depth is 6 meters, and the length of the streamer is 3 kilometers, and the sampling interval is 4 milliseconds. So all these parameters are very useful, like when you perform the actual seismic data processing. So these are used for designing and defining different parameters in your data processing. Okay, so once you have that segvi file downloaded, seismic.segvi, you need to read that in Seismic Unix and change it to seismic.su. Su is the Seismic Unix file format. So this is what Seismic Unix can read. So you have, first step is to convert your seismic.segvi file into Seismic Unix file format, and then you can apply gain on it. So you can apply a t-squared gain. So you need to check these parameters to make a good balance. And then as a quick QC, you can display your short dataset as a movie. So this script is for having a quick review of your dataset as a movie. And then if you want to review your source and receiver positions, you can use this command, you can use this script. And QC stacking chart available receiver positions for each CMP. So you can also generate the receiver positions for each of the CMPs using this script. So this is just like to do a quick QC of your 2D line. The most important thing is you have to convert that into Seismic Unix.su format, and then you have to apply gain to visualize the data. Okay, and if you want to check which headers exist in your file, so you can just run this command su-range on this seismic.su file. It will give you all the headers that exist in this file. So basically EP is the shot header, so you have got shots from 101 to 1112, and the CDP and CDP-DT header, and then offset, the receiver elevation, the source elevation, and the source and receiver coordinates. NS is the number of samples in a trace, DT is the sampling interval. So yeah, you can visualize them using the su-range command. Now let's visualize some of the data sets in this line. So this is to show you the display of the shot gathers. So only 5 shot gathers are displayed here, so you can use this script to display the shots. So you can see the direct travel energy and some multiple energy here, and you see some noise here. So yeah, and you see some negatively dipping noise here. So yeah, you can visualize them to QC your data if there is any noise in it. And this is a common near channel display, so you can use this script to generate the common near channel. Yeah, and then you can also generate the frequency panels. So frequency panels gives you a good indication of which frequency panel is affected by noise. So here you have got up to 10 Hertz here, and here you have got from 15 to 25 Hertz, and this is the full bandwidth of the actual shot. And then in the next slide you have got 30 to 45 Hertz, and then 45 to 125. So all the higher frequencies are here. So you need to boost, you need to scale the higher frequency in order to visualize them, which is not done at the moment here. Okay, this is the FK spectrum. So on the left is the shot gather, and on the right is the shot. So you can see some of the energy is aliased here. So basically you can get rid of the aliased energy by interpolating further, like 2:1 or 3:1. So in the next slide, like after interpolating here, like n inter equals 2, so it's 2:1 interpolation, you can basically remove that aliased energy. So that aliased energy is de-aliased now. So yeah, you can do that in Seismic Unix, that too. And if you want to apply NMO correction on the shots, so you can either use different velocity time pairs, or you can use a constant velocity to apply the same velocity everywhere. So here you have used pairs of velocity and time. On the left is the shot, and this is the NMO corrected. I think when you apply the NMO correction in Seismic Unix, it applies a mute for the stretched energy. So when you apply the NMO correction, the energy is stretched, and this S mute factor controls the energy that is muted. Okay, so you can also perform autocorrelation. So this is a common channel near channel display, and when you do the autocorrelation, this is the autocorrelation display. It's actually displays both the negative and the positive side. We normally don't display the negative side, so we just display from the positive side. Yeah, and you can also create a near offset stack, so you can select near traces from each of the shots and then stack them. So this is how it looks like after stacking. So this is a near offset stack. So if there is any noise sitting on the near channels, it will pop up on the near offset stack. It will easily be visible. And this one is to demonstrate that you see there is something sitting in the water column, so you can apply a mute above the water bottom. So yeah, this is after the mute. Okay, so that was all about some of the QC displays on the real seismic data. Now this is a typical marine seismic data processing sequence. So you start with your raw SECD or SECY tapes. You have to reformat your data to whatever format your software accepts, and then you do the pre-processing where you apply some kind of noise attenuation, resampling, and all these things. And then you need to apply, you need to do the multiple attenuation. You remove all the water bottom related multiples and the other multiples using radon. Then you have to regularize your data and interpolate. You perform the migration. You need to do the time velocity or the depth velocity model building, performs migration, yeah, and then finally you produce the processed stack. So yeah, this is a typical marine seismic data processing sequence, and not everything, but you can do quite a lot of these things on a small 2D seismic data set. So using Seismic Unix, so it will be a good package to start learning things in practical. Well, that's all for now. If you have any questions, if you have any question, you can just message me directly, or you can leave them in the comment box. I will get back to you as soon as I can. And good luck. Thank you for watching.